One of the most important biological applications of the acid-base equilibrium system is in buffers. And we use buffers in our blood to maintain a certain pH because we don't want our blood pH to be completely thrown off if we're to drink a glass of lemonade. So buffers are substances that resist pH change, and they do that by neutralizing any acid or base that is added to them. So a buffer consists of either a large amount of weak acid and its conjugate base, or a large amount of weak base and its conjugate acid. So the common buffer that we have in our blood, the common buffer system, is that of carbonic acid and its conjugate base. So let's write the equilibrium reaction for that acid in water. We have the carbonic acid in water, and that creates H3O plus and HCO3 minus. So that H2CO3, or the carbonic acid, is the weak acid in this equilibrium reaction, and the HCO3 minus is the conjugate base in this equilibrium reaction. One thing you may notice when you start doing buffer calculations is that it might not be very obvious what the conjugate base is. It might not show up as a negative ion or an anion. It may be represented in the form of a salt. So this sodium is attached to the anion, for example. Sodium or potassium are cations that might be attached to those conjugate base anions. So just be aware of that and know that it's fully soluble. So however much of that salt is present, that's going to be the same concentration as your conjugate base. Now, if we add acid to this system, this buffer system, that is going to react, those H plus ions, or the acid part of that, is going to react with the conjugate base to make more carbonic acid. And if we add acid to this system, more carbonic acid, or that weak acid, will be produced. Now, if we add base to this system, it's going to react with the weak acid and produce that HCO3 minus anion. So if we add acid, it gets neutralized by the conjugate base, and if we add base, it gets neutralized by the weak acid. That's how the pH is able to stay so stable, because there's just neutralization reactions happening when you add acid or base to this system. So this is what a buffer system looks like. Now let's learn how to calculate the pH of a buffer solution. And this practice problem has us calculating the pH of a solution that is a 0.100 molar acetic acid solution mixed with a 0.100 molar sodium acetate solution. So this is our buffer system. Now what I'm going to do is I'm going to start out by writing out just the acid equilibrium, so the weak acid equilibrium reaction. So I have that acetic acid in aqueous solution combined with liquid water to create the hydronium ion in aqueous solution and the acetate ion. So this is my acid equilibrium. One thing you're going to notice about this equilibrium equation is there are two sources of acetate ions. One is in that acid-base dissociation, and the other is in the sodium acetate, that salt solution, that 0.100 molar salt solution. Now the Ka for acetic acid is 1.8 times 10 to the negative fifth. I'm going to use this Ka in a little bit. But first I'm going to write out my reaction here. I'm going to leave out the water because that doesn't participate in our equilibrium constant expression. And then what I end up with is the acetic acid in equilibrium with the H3O plus ions and the acetate ion. My initial concentration of the acetic acid is 0.100. The initial concentration of my hydronium is about 0, and the initial concentration of my acetate is 0.100 moles per liter. And remember, that acetate ion concentration, that comes from the sodium acetate that's also in that solution with the acid. So the salt and the acid are together in that solution. I sum up my totals to get my equilibrium concentrations, and then I can use those totals in my equilibrium constant expression, which I'm about to write out here. So the Ka is 1.8 times 10 to the negative fifth, and that's going to be equal to the concentration of my hydronium ion times the concentration of my acetate ion, so the C2H3O2 negative ion, over over the concentration of my acetic acid, so the HC2H3O2. So 1.8 times 10 to the negative fifth. Now I'm going to substitute my values in here, those equilibrium concentration values, and I get X times 0.100 plus X over 0.100 minus X. All I'm going to do now is solve for X because I want to know ultimately the pH, which means that I want to know the hydronium concentration. Now, one assumption that I can make, or approximation, is that because the Ka is so small, the X values are also very small, so if I'm adding them or subtracting them from a value, I can eliminate those from my equation. That makes life so much easier for us. The next simplification that I can make is I notice that I have 0.100 and 0.100 on opposite sides of this fraction. So guess what? I can eliminate those from this equation as well. That makes life even more simple for us. So really, X is equal to 1.8 times 10 to the negative fifth moles per liter. That is my hydronium concentration. So all I need to do now is just solve for the pH. So the pH is equal to the negative log of 1.8 times 10 to the negative fifth. So I type this into my calculator. Negative log of 1.8 times 10 to the negative fifth is equal to 4.74. So the pH of this buffer system is 4.74. Remember, this is a buffer system because I have a weak acid and a lot of its conjugate base in the form of a salt, but it's still there as that negative ion, that C2H3O2 ion. Now here I am calculating the pH of a buffer that results from the mixing of 60 milliliters of a 0.250 molar HCHO2 solution and 15 milliliters of a 0.500 molar NaCHO2 solution. So I have a weak acid and its conjugate base in the form of a salt, but it's still there. I'm going to write out the acid equilibrium here. So that acid combined with water gives us hydronium, and then the CHO2 anion. The equilibrium constant expression for this reaction is the concentration of the hydronium times the concentration of the CHO2 negative over the concentration of the HCHO2. So that's all going to equal 1.8 times 10 to the negative fourth because that's the Ka of HCHO2. So I'm going to write out my reaction to fill out my ice table. So HCHO2 in equilibrium with the hydronium and then that conjugate base, the CHO2 minus. Now one thing I'm going to keep in mind here is that I don't have initial concentrations. All I have are volumes and concentrations of different substances. So if I have 60 milliliters of a 0.250 molar HCHO2 solution and I combine that with 15 milliliters of another solution, the real concentration, the real molarity of my final solution is found using the dilution equation. So I take 60 times 0.250 divided by 75, and I get 0.2. So what started out as a 0.250 molar solution of acid goes down to a 0.200 molar solution of acid because we diluted it with some of that salt solution. Now then I figure out the molarity, the new molarity of the salt solution doing the exact same thing. 15 milliliters of a 0.500 molar salt solution and then that's diluted to 75 milliliters. So the true final molarity of that salt solution is 0.100. And then we have about 0 molarity for our H3O, our hydronium concentration. Now the reason we had to do this was because once we mixed these two solutions together, the total volume of this solution changed. So we needed to know the new molarities with that total volume after mixing. So with the 75 milliliters instead of the 60 or the 15 milliliters. Now the changes are found using the stoichiometry or the coefficients. So we have the negative x's and the plus x's, and then I rewrite or sum up my columns, so I get 0.200 minus x, x, and 0.100 plus x. So my equilibrium constant expression, I substitute the values in, so I get 1.8 times 10 to the negative fourth equals x times 0.100 plus x over 0.200 minus x. Now the Ka for this is pretty small. It's not that small, but it's small enough where I can make the approximations of removing the plus x and minus x from my equations, and that makes my math a whole lot easier. So I'm just going to cross multiply here. I have 0.200 times 1.8 times 10 to the negative fourth, and I get 3.6 times 10 to the negative fifth. So 3.6 times 10 to the negative fifth is going to equal 0.100 times x. So I'm going to divide both sides by 0.100 to get rid of that and get x all by itself. So then x will equal 3.6 times 10 to the negative fourth. So x equals 3.6 times 10 to the negative fourth. Now what we really need to do is figure out what that x really represents and what we need from this equation here. So this whole thing is asking for the pH, and the pH is found by taking the hydronium concentration. So I plug the hydronium concentration into that logarithmic equation. So negative log of 3.6 times 10 to the negative fourth is equal to 3.44. So the pH of my buffer solution is 3.44.